Hello everyone, it's Wisteria. In the last lecture, we discussed about the definition of statistical mechanics and the comparison between statistical mechanics, kinetic theory of gases, and thermodynamics. Why we should use statistical mechanics instead of the other two. So that was the basic outline of statistical mechanics, and basic introduction can also be said. Today we will be talking about microscopic states and macroscopic states. In the last lecture, we have used the terms that macroscopic or microscopic, etc. But we might not know what are they, why do they call what we call them. So in this lecture series today, we will be talking about them, the macroscopic and microscopic states. To define macrostates and microstates, let's consider a system of volume V. This physical system contains a volume V. And it have n number of particles when the order of n is 10 raised to 23. You can assume how large the number is. Now, this is a system with which we deal. These systems can be classified into two types. One is the extensive properties and another one is the intensive properties. And we have to deal with the extensive ones like entropy. Now, these extensive properties do depend on some variables of this very system, and they are N, V and E. Why and how we will defining now. So as for the first ones, N and V, we will be taking a limit, the thermodynamical limit, which is nothing but thermo The thermodynamical limit is nothing but when n tends to infinity and V tends to infinity. Thus, the number density n upon V remains same as its predefined value. Now, in this thermodynamical limit, what we have seen that the extensive properties are directly proportional to the size of the system. And the size is defined by n, the total number of particles into the system, and V, the volume of the system. It is experimentally observed, of course. Thus, we can say that the state in which the system is now at this very moment depends on N and V. So, from here, N and V's dependency has been explained. So, the remaining one is the energy. Now, the system contains n number of particles. So, we can say that there are a lot of particles like 1, 2, 3, 4, so on until n number of particles are there who have Ni who have a definite energy somewhat like E1, E2, E3, E4 and Ei. The summation over all these particles who have those number of energies like 1 plus 2 plus 3 plus 4 plus Ni is nothing but N. So, from here we get to this conclusion that total energy E, the total energy E is equals to summation over I Ni Ei. Now, from quantum mechanics we know that these Ei values are not continuous. They have a definite gap between two definite Ei's, like E1 and E2 have a gap between them. Similarly for E3 and E2. If that's the case, then we can say that all possible values of E are also discrete. But in case of systems of large volume, we can see that we have seen that the gap between two successive energy values are very small. Thus, it seems that the total energy E is continuous to some extent. Thus, from here we can say that the state of the system can also depends on E. Now, the specifications of the value of N, V and E defines a macrostate of a given system. The specified value of these three defines a macrostate of a given system. This is how we define a macrostate. So, what is microstate? So, let's start with an example to understand what is microstate. Let we have three energy values like E1, E2 and E3. These are the energy values of three particles that is in the system. Thus, the total energy will be the summation over them. right? Now, if we consider the possible combinations that can be done with them, like we can write it like E2 plus E1 plus E3, or like E3 plus E1 plus E2. There are so many combinations that can be written for us for a large number of particular system, and these combinations are microstates, the possible states of a system. That constructs the macrostate. Upon summing the all values, we will get the same E, but the combination or the process how we are summing them, the series are not same for each cases, so they are different from one another, but they are giving us the same macrostate. Thus, they are different microstates. This is how the macrostates and microstates are defined and related to each other. Now, we can identify various microstates by independent solutions of the Schrödinger equation of the very given system, considering eigenvalue E of the relevant Hamiltonian. So this was it for today. Hope you like it. If you like the video, leave us a comment. If you don't understand anything, please tell us by a comment. And don't forget to like, subscribe, and share to your friends. Goodbye.